Thank you for this opportunity. Basically, today I want to introduce my current work with Dr. Ian Stevenson. That's the similar topic, tracking the fast and slow synaptic networks by neural spiking data. Basically, now this is a synapse, and as I mentioned in Julian, there's a short-term plasticity, and which is a story about a neuron transmitter release, and long-term plasticity, which is about the post-neuron receptor. And if we record the spiking activities for both pre and post neuron and plot the cross-correlogram, we can detect some coupling patterns between them. This is one example from Swartz's lab. In this cross-correlogram, we can see that after some time delay, there's a peak here. That means the post-neuron fires nearly immediately after the firing of pre-neuron. And based on previous research, actually the coupling pattern or coupling weight will change along the time. And this changes occurs in different time scale. In the scale of millisecond, the short-term plasticity will give us the short-term changes. But for the scale of around minutes, things are more complicated. The long-term plasticity obviously will give us the long-term changes, but there's another very interesting but annoying long-term changes, which is actually caused by the short-term plasticity. This is now one example, and also from Swartz's stuff. We can see there's a long-term fluctuations in pre-neurons, and we can also see the more pre-neuron fires, the less the probability of the post-neuron will fire. That means there's a short, the depression STP. So because there's a depression STP and long-term fluctuations in pre-neuron, you will produce long-term fluctuations in post-neuron. So basically, our goal is to use the spiking activities or spiking data to track both short-term changes and long-term changes. Also, as I mentioned, also want to distinguish this kind of long-term dynamics from the LTP. So to achieve these goals, we basically build a model based on the Poisson GRM. At each time TK, the equation is like this. The log link was used to capture the nonlinearity. And for the linear component, it basically can be divided into 3 parts: the long-term part, the short-term part, and the synaptic connection, which give us the shape of the coupling effect. To fit the synaptic connection, basically we just need to fit the shape of the cross-correlogram by alpha function. So our focus now is to fit the long-term part and the short-term part, and how to combine these two. So let's focus on the long-term effects, which include the baseline and long-term plasticity. Here we choose to use a point-precise adaptive smoothing to handle this. It has 2 steps. The first step is filtering, and the second step is improve the estimation from the first step by backwardly smoothing. To do the filtering, we first need to define the evolution of the long-term effects. If we denote the long-term effects at time tk to be theta k, then and we assume it evolves like this with some Gaussian white noise. The basic idea for the filtering is that we first now predict at each time tk, we predict the parameter by this equation, and then correct our estimation by the real observation. And another thing I want to mention is that the pre-specified covariance Q will influence the estimation a lot. If we set it to be too small, the estimation will be too smooth. If we set it to be high, the estimation will be super noisy. But for short-term changes estimation, the smoothing can no longer be used because the STP is changing so fast. If we use smoothing, we can never detect anything. So the idea, I think, is very similar to the Julian. Basically, we handle it by additive effects that depends on the presynaptic interspike interval. In short, now we just convolve this modification function along the presynaptic spikes. What do I mean? Maybe take the depression STP, for example. This is a so-called modification function for STP, which is a function of presynaptic ISI. When there's a spike in preneuron, the STP will decrease sharply, and the amplitude is determined by this modification function. For example, now the ISI is small, which corresponds to the blue dot. And then after that, the effect decays exponentially with rate tau. And then if there's another new pre-spike, additive decrease and then exponentially decay, so on and so forth. So the basic question is how to handle this modification function. Here we just now choose to use a linear combination of basis function to capture the nonlinearity. So by doing this, the STP estimation just reduced to a linear model problem. Okay, so now we have a method to deal with these two points separately, and we choose to combine them by alternating optimization. That means, for example, we first fix STP and estimate long-term pot, and in the next step, we fix the long-term pot and estimate STP, and then keep going on this process until the model events converge. So now we have the model like this, and we have the method to fit our model. The next step is to use some simulations to make sure that we can handle different situations. In those simulations, we play around different STP. All the baseline is assumed to be is generated as the constant, and the LTP is generated as stem changing at mid time point. And this column just shows that we can handle it very successfully. Now we fix the STP to be depression and simulate data as linear change for the simulate the long-term plasticity as linear changing or sinusoidal changing. Things mostly looks good. But the linear changing and sinusoidal changing LTP is far from real situation. So how about now the estimation for some more realistic LTP? In this simulation, we choose to use the STDP model to generate LTP. In that model, the LTP is assumed to depend on the presynaptic spiking time. And in this specific example, we use a double exponential function as a modification function for LTP, which is very common for cortical and hippocampal slices. Under this model, we can generate the LTP as shown in this black line, and it also looks good. But here, another thing I want to mention. Obviously, we can use the STDP model to model the LTP and estimate this kind of modification function directly. And actually, some previous research really did this. But the LTP, it actually depends more than the presynaptic spiking time. So here we just want to give an unbiased track for the LTP. How about the estimation on the different firing rate? Actually, the presynaptic firing rate will influence the estimation a lot. In those simulations, the baseline for the post-synaptic neuron is set to be constant. But we can see if the presynaptic firing rate is high, get a not accurate estimation for LTP. If it's low, then the LTP estimation will vary a lot. So basically based on these simulations, we are more confident that our method can handle different situations. But there are some problems remaining to be answered. The first problem is that, do we really need to do all the things simultaneously? Can we just estimate them part by part, which will make our life easier? But unfortunately, we must do this. This just show one example. In the first column, everything was estimated simultaneously, and things looks good. But now if we miss the baseline estimation, the fluctuations of baseline will flow and even enlarge in the LTP estimation. Similarly, if we miss the STP estimation, the fluctuation of the STP will flow into the LTP estimation. So in brief, if we miss any part of them, maybe the overall estimation will be good, but we'll get the spurious estimation in some other part. And also this plot just give an answer for the this goal. Yes, we can distinguish this kind of long-term, the long-term changes not induced by the STP from the LTP. Okay, that's the basic ideas for our current work. Are there any questions?
Thank you very much for the wonderful talk. And so we have one question from Danielle, who asks, how are you able to tell from extracellular recordings whether a cell is presynaptic to another?
Excuse me, can you, the recording? You mean the spike sorting problem, right? I'm not very sure, sorry.
Yeah, I think this is a more, I'm not sure about the question either. So basically here, your model is basically a statistical.
I see. I think now this question is more about the spike sorting problem. And in our model, we assume everything is not perfectly sorted now. We just know which spike belongs to which one.
Yeah, that's what I'm gonna say. So in the model, you would assume you know the perfect mapping. Like you are just assuming that you have two cells, you know them, which one is presynaptic, which one is postsynaptic. And
exactly.
It's possible to tell from the experiment is I think beyond the scope of this talk, right?
Yeah.
I mean,
yeah.
Kind of. I know I'm really impressed how, like from your mathematical formalism, I can totally see how a point process adaptive smoothing, or is that what you call it, could produce long-term changes in synaptic weight. But I mean, whatever shape of long-term synaptic effects you would be able to reproduce. But I'm just wondering a little bit more about the possible biological mechanisms for this. I know Giuseppe is probably going to touch upon it later, but Ganchao, what would be your guess based on your work? So is it only, so does STDP completely, if you do a simulation with a network of neurons with only STDP mechanisms, would it capture the statistical predictions from your theoretical?
So you mean the multiple synapse case or multiple neuron case, right? Or a network of the...
Well, just maybe two neurons, presynaptic, postsynaptic. If you only assume, if you simulate their spike trains and you only impose STDP, would it reproduce would it match your expectations from your theoretical?
Actually, now, if we know the true LTP or STP and turn off this estimation, we can obviously we can recover the estimation for any port. But now it's very hard now to distinguish those two ports separately by experiment.
Okay, I have follow-up questions, but I think we need to move on. Thank you very much.
Sorry, thank you.
So next up we have